happens when light, not why, look at that. I said when, and I wrote why, because I was thinking light, and the I from light messed me up. When light waves hit matter. So when light hits the desk or the pencil in front of you, or it hits your little dog at home and it shines into your eyes, what actually happens there? What's going on when light hits things? So to figure this out, we kind of have to look at matter on a very small level. Because light waves are very, very tiny. So we have to zoom in and remember that everything is made of atoms. So if we look at an atom, let's draw a little atom here. It doesn't matter what atom it is, so we'll just a general atom, okay? And let's put some little electrons and things around it. Now we know from our sort of studies, I'm going to draw little red dots that represent the levels of energy that electrons can have. So there's the first energy, we call it the first orbital, right? And usually we have 2 electrons in there for, well, 1 for hydrogen, 2 for helium, right? The energy levels. And I'm going to draw another energy level out here, which is the second energy level. And when we do the Bohr-Rutherford model, we learned that, you know, they can hold 2 and then 8 and then 8. So this is just drawing a picture of the atom according to the way we learned about it in grade 9. These energy levels in the more modern quantum theory, remember we talked about them being the s orbitals and the p orbitals and the d orbitals and that kind of thing. But this is a nice simple picture to get the idea. Now let's just draw in green here a little electron who lives on one of these orbitals. Let's say he lives right here. Okay? So that means that electron has that much energy. That's why he's on that level. Okay? It's not like a planet going around the sun. It's not like that. It's just a diagram to show that that's how energetic this electron is. Okay. So he's sitting there and he has a certain amount of energy. Remember that energy is associated with the vibration of particles and the way that they move. So this electron is grooving and dancing with his little bit of energy there. All right? Now let's think about what happens if a light wave comes along. And I'm going to draw this as a blue light wave, just for fun. Okay? A blue light wave has a wavelength, right? And the wavelength is the space or the distance between the bumps. If this blue light wave has a wavelength that's just the right size, remember that wavelength, or the distance between the bumps, tells us something about the energy that the light wave has. So you'll have to remember this from a previous lesson. Let me just go down below to scratch a few notes. Remember that a wave like this that has a very short wavelength has more energy. Let's put the word, I was going to put higher, but let's put more energy. And a wave that has sort of bigger wavelength, more space between the bumps, has lower energy, or less. I guess I could write less energy. So the size of the bumps, right, the wavelengths, can tell us or show us very quickly how much energy a wave has. And of course we could measure it. And we can measure it. We have mathematical equations that can tell us exactly how much energy there is if we know exactly how far it is between the bumps, if we know the wavelength. So it's pretty easy to do that. Now you can get all kinds of energy. So, you know, this wave would have a certain amount of energy. This one would have more. And this one would have less. But what's interesting is each wave of light has different amounts of energy, but so do the levels in the atom. Let's look at this. Go back to our picture. The energy difference between these orbits, the energy to go from here to here, that's a certain amount, right? Let's just say for fun, let's just use the amount 10. Let's just say it's 10 to go from there to there. right? Now, the interesting thing about electrons is they can't go anywhere. They have to be on one of the levels, right? So if this little electron gets a little bump because a little wave comes along and makes him dance a little faster, he may or may not get enough extra energy to sort of bump himself up to that level. But let's just imagine that this wavelength right here is enough. Let's say it's 10. So this blue light has an energy of 10. And when it wiggles along in here and this electron hits it, this electron feels that wave. And just like you do at the wave pool, he starts to bob and shake along the wave. He gets the energy of the wave. What we say is, we say he absorbs the energy. So when a light wave makes something dance, we say that it absorbs the energy, right? The wave energy has gone into the electron, and we can see it in his increased movement, shaking and dancing. Now, if this blue wave has just the right wavelength, the right size to make it, let's say, 10, and if the distance from, or the energy between these two levels happens to be, say, 10, well, then this wave will cause this electron to have just enough energy so he will jump. And we would have to write him up here now because he has more energy. So it's like he jumped a level. We say that he's been promoted. The electron has been promoted to a higher energy level because he absorbed the energy from the blue light wave, and it was just the right amount to bump him up. It was 10. Now, if this was only 8, he wouldn't be able to jump. He wouldn't be able to jump. And so what would happen is the wave, it might not even wiggle him. It might not be enough. He might just not even notice it, right? Or he might just become a little bit more energetic, but not enough to actually get to the next level. So it would not be something we would notice. Now, the problem is, if you remember the rules, there's already electrons in that level. Let's say there's already electrons all around there, right? And remember that when we talk about the quantum model, you can only have 2 in every energy level. So even though there's 8 in this level, there's the S and the P and the D, right? But I could draw 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Well, those electrons are already in that energy level, and when he gets bumped up to that energy level, they all look at him and say, "What are you doing here? This is full, get out." There's too much energy now, right? There's too much going on here. You can't stay here. So that electron immediately has to jump back to where he came from to keep the atom stable, right? Remember, stability, the pattern of these electrons is very special. It keeps the atom in a stable state. So he has to jump back. Well, in order to jump back, he has to get rid of that energy that he got. So guess what he does? Remember that if an electron moves, if an electron wiggles, it makes a wave. So when he moves back down, that wiggle makes a new wave. It's like he's a cork in the water. And by pushing down to the next energy level, he makes a new wave. That takes off. Now, I should have drawn that. I'm sorry, now that I see it, I should have tried to draw exactly the same as the one going in with exactly the same wavelength. So let me just make it sort of look exactly like that one. That's what's important, okay? This over here is still exactly the same as it was over here because it's the same amount of energy, right? So the story is the wave comes along. It has just enough energy to bump that electron to the next level, makes him dance a little faster, and up he goes. But it's crowded up there, so he has to drop back again, or else the atom will be in what we call an excited state, and it doesn't like that. Atoms like everything to be sort of low, lowest possible energy, right? The atom's motto is chill, calm down, not excited. So he has to jump back. But if electrons wiggle back, when they wiggle, just like a cork in the water, they make an electromagnetic wiggle or wave. And that wave will have exactly the same, we called it 10. Doesn't matter. It's not really 10. It's just a number I used to make it simple for us to understand. And so look what happened. If you were looking at this this blue light wave hit the electron. He jumped up to the level. He jumped back down and made a new blue wave exactly the same. It looks like the wave of blue just bounced off the atom, doesn't it? It looks like the wave just hit and bounced. If we can't see this detail right here in the middle of this promoting of the electron and moving. But see, there's a wiggly electron involved here. And that's how this second wave gets made. So we call this a reflection. We call it a reflection because it looks to us like the blue ray just bounced off, but it's actually not. The blue ray that went in got absorbed by the electron, caused him to jump up, then he jumped back and made a whole new wave, but it still looks the same to us. So we call that reflection. Okay? Now, what happens if it's not blue light? What happens if on the same picture I have some green light? If green light, now green light, remember, has a little bit longer, it's a little bit longer than blue, so I'll draw it longer. What if that comes up and hits? Well, the problem with green light is that the green light has too big a wavelength, so it means it has less energy. It's not enough for that electron to jump. And if he doesn't jump, he can't jump back, and the green light can't be made again. So what happens to the green light? Well, for this electron, the green light would basically just pass. It wouldn't really do much at all. But that green light might hit another electron in a different energy level. And to do this, I need to add a few levels. So I'm going to add another level over here, and maybe another one way out here. Maybe that green light is going to hit an electron up here. And this is so the first electron was jumping here. That was 10. This electron, though, could jump up here, but this is not 10. This might be 7. Smaller number. So the green wave could make him jump, but the blue wave could not. The blue wave can make him jump, but the green wave cannot. Now, because 7 is lower, then what can happen is this guy might jump like this, and then he might jump back, and then the green light might be reflected. So an atom can reflect different kinds of light depending on where or which electron the lights are hitting and which orbit or orbital energy level it's jumping to and from. So if this was the green one, he might make a green ray when he jumps back, and that green ray would then be reflected as well. But what happens if none of the electrons can jump? What happens if when the light hits it, the electrons don't jump? Well, here's an interesting thing. Sometimes the energy is not enough to jump a level, and so all it does is just kind of make the whole atom wiggle a bit. Okay? So let me just go back here. We'll go down and we'll draw another atom. Okay? Maybe this is a different atom. And so, you know how we said the blue light was coming? And we used the number 10 to describe it just for fun. Well, here's the electron, and here's another one. And none of the electrons are like 10. Maybe 10 is not enough to jump any of them. And so what happens is the blue light goes in, and it might cause the whole atom to wiggle and shake. So these are just shaky lines, right? The atom might vibrate or shake in a more vigorous way. And what that does is it becomes heat, okay? So what happens is this blue light might cause heat instead of a reflection. The atom would get warmer. And so that would mean that the electrons were producing very, very low, what we call infrared waves, right? Infrared waves caused by the jiggling and shaking. But we can't see that. So if the blue light comes in and it doesn't have enough to make an electron jump, then it can't produce a new blue wave. But it can cause the atom to wiggle and shake, and that wiggling and shaking can produce the lower energy infrared waves, which is now heat. But we can't see it. So in this case, it's almost like the blue light just disappeared. The blue light came in, but what came out was something we can't see. And so we say that this means the light was absorbed. So there's two things that can happen when a light ray hits matter. It could be just right to make electrons jump orbitals, in which case they jump back down and make new waves, and it looks like they bounced. It looks like the waves bounced off. We call that reflection. But it's also possible for the waves to hit the atom and not really make any electrons jump across levels. And so what happens is the electrons are wiggly, everything's wiggling. They wiggle a little more, but it's not enough to move to a higher level, and their little bit of wiggle produces a infrared wave, which we cannot see, right? We can't see that. So there's still something actually bouncing off, but it's just because we can't see it, we say that the light has been absorbed. So that's a very important concept when we start to look at colors. The difference between light that is absorbed or turned into heat and light that is reflected, which appears to bounce off. Okay? Good. Let's talk now about colors. So let's now talk about what makes things appear different colors. Well, colors, there's a problem with colors because there's color in terms of the human experience, which our brain and our eyes interpret for us. But there's also color in the physics world, which is basically an intrinsic property, which means it's built into things. And it's not, you can't argue about it. So two people could look at this color that I'm going to draw on the board right now. Right? The two people could look at this color. And one person would say, well, I call that brown. And someone else says, no, I call it orange. Right? And they can disagree. But a physicist can call it a very specific color that never changes, because for physicists, if you remember, color, red, orange, yellow, green, you see what's changing, right? Blue, violet. Red light has to have bumps this far apart. So if it has bumps that far apart, it's red. I don't care what it looks like in your brain. Physicists call it red. And if it has bumps this far apart, we call it purple or violet. And if the bumps are this far apart, we call it green. So the wavelength, remember that's called the wavelength, right? Lambda. The wavelength in physics equals color. That's what color means to a scientist. But to human beings and to people who look at it more from a sort of experiential, emotional kind of way, they don't know anything about that. They just argue back and forth. Orange, no. Brown, no. Orange, no. Brown. And some people may say, I think it's pink. Well, wait a minute. Some people have problems with their retina, and they would look at that and they would say, what are you talking about? Like, I don't know, it looks black to me. Who knows? So there's color in terms of how people see it, but there's also color in science, which is very specifically just a measurement of the wavelength of the wave. Okay? All right. So now that we've got that out of the way, let's look at how humans see color. So first of all, remember Isaac Newton? I'm just going to erase all this stuff. It'll just be faster. Remember Isaac Newton? And he did this interesting thing. He took white light. Now I can't really show white on the board, right? So I'm going to use a black line to show the beam of white light, which is a little bit strange. So he shone the white light like this towards this prism. So we're going to write white light here to remind us. Right? He probably did it by putting like I said, putting a screen on a window with a tiny hole poked in it so he could get a little bit of sunlight sort of shooting through the hole in like a little beam. And what he noticed was that when it hit the prism, it began to bend. Because waves can do that. And so it bent, sort of like this. And when it bent, oh, you know what? That's too big. I'm going to run out of room here. I need my small. Yeah. It started to bend. The red bent. Actually, the red bent the least, I think. So let me erase that. Carefully. Actually, I think I can just do it this way. There. Okay. So when he bends it, the red bends a little bit. Oh, I did it again. Rats. I wish this would just remember what I want. But the orange bent a little bit more. Or a little bit, yeah, red, orange. And so yellow. What happened is green. I'm just going to forget about trying to get the small lines here. Blue, violet. And so what happened was this. The white light that was shining in was bent into all the colors of the rainbow. And maybe you've seen this at home. If you have like a chandelier above your table or a crystal of some kind, anything that is plastic or glass that light can go through, but it bends, you get little rainbow effects. Have you ever noticed that? You get little rainbows on things that when the light hits them. And this is because of an interesting property of light rays. But what it showed Newton was that, hey, wait a minute. White light is not really a color at all. White is not a color. It's a mix of colors. Light is a mix because we've been able to separate them out using this prism, the rainbow effect. So that's an important thing to remember, that white light is a mixture of colors. So now, here's an interesting thing. If white light is a mixture of colors, then that maybe explains how when we sit in a room like this and we look around, it's pretty much white light that comes out of the light bulbs or the sun. But the light that bounces back to our eyes off of things, sometimes I see red light, but no green, or I see blue, I see the colors. And remember, the reason for that is because when white light strikes something, it's actually a mixture of all the colors, but only some of those colors have the right wavelengths when they hit the atoms. Only some of those colors can cause the electrons in that thing to jump and reflect the color back. So if white light hits something, the nature of the electron arrangement inside the substance, let's say it's this book right here. I have a blue book here, blue binder. All the white light hits it, but only the blue light is the right size to make the electrons jump. Then they jump back and they spit blue light back out again. What happens to the red and the orange and the yellow? It turns to heat. It turns to heat, which I can't see. So that's absorbed. So the molecules in this book that I'm holding, here, let me just draw this. I'll go back down. Let's just draw a blue object here. So here's an object that's blue. Okay, so all the colors of the rainbow are hitting it. All the light is hitting it. So if white light comes in like this, now I know it looks black, but remember, this is white. The blue light has just the right size. Remember the wiggle? Just the right size. It goes in, it makes electrons jump, they jump back, they make a new wiggle, and the blue light reflects back towards our eyes. So over here, I'll draw our eyes. Here's a little eyeball, sideways eyeball, right? Blink, blink. And we say, oh, I'm seeing blue light. But the orange and the red, right? So the other colors, they're also coming off. Whoops, let me turn that to black. The other colors, I'm going to put other colors here. are not enough. They're not the right size to jump the electrons a full level. So the electrons don't jump and jump back. Instead, these other colors turn into heat. That's why objects get warm when light shines on them. Right? That's how things get warm. In order to get warm, you got to jiggle more. So the waves of the other colors are causing the whole atoms inside there to jiggle and get more energy, but they're not causing electrons so much to jump up and down. And we say that it turns to heat. So we say that they are absorbed. And if they're absorbed, we can't see this heat coming off. So they're gone. The yellow's gone. It's turned to heat. The red's gone. It's turned to heat. The green is gone. It's turned to heat. The only thing that bounces back is the blue. And we say, oh, that book is blue. And it all depends on the molecules inside the book. So the color that we see things depends on the molecules inside it and which electrons are going to jump and bounce and which color is going to bounce back and reflect and which colors will turn to heat. Okay, so now we can think about colors in terms of how our eye sees them. So in our eye, there's a retina. And we've already talked about this, so I'll just review it. The retina has special cone cells, remember, that are sensitive to red light, blue light, green light, and blue light. That's all. That's all there are. Red cone cells, green cone cells, and blue cone cells. So, if we have a blue object, I'll just reiterate this blue object here. Okay. Now, white light, to symbolize white light, I'm going to use red, green, and blue as a mixture. So that's really what white is. It's a mixture of all three. It's actually a mixture of other colors too, but we'll get into that in a second. Okay, so the red, the green, and the blue are the three colors. We call these the primary colors, red, green, and blue, because our eye is set up to see them, primary colors. Now, some of you take art, and you're like, wait a minute, I thought red, blue, and yellow were the primary colors. Well, hang on to that, because they are the primary colors if you look at this whole story sort of from a different perspective. Okay, so we're looking at it at a perspective where the primary colors are red, green, and blue, because that's the ones our eyes can see. All right, so let's think about what happens. So the blue ray gets reflected because the electrons are just right in the paint on this book. Right, the dye that's in the book is just right. The electrons are in the right spot where they'll jump a level and they'll jump back for blue light. But the red and the green, they just go like this. I'm just going to go like this, right? When I do that, I mean those turn to heat. So we do not see them. They are absorbed. So we don't see anything coming back. And the eye only gets the blue and says, oh, it's a blue book. A book is blue. Okay. Now, you can imagine a similar picture if the book was a different book with different dye and different chemicals, maybe they would cause the green to bounce back. And then the blue and the red would turn to heat. So we could draw another picture over here, just very, very quickly, and draw the red light, the green light, which is all part of white, right? So when we see this, all three together, we have to imagine that's what white light is. And this time, it's got different molecules. The electrons are in different positions. And the green light is the one that causes electrons to jump. And it bounces back to our eye. Whereas the blue and the red, bzz, they turn into heat. Bzz, turn to heat. So they are absorbed. We say blue is absorbed, red is absorbed, but green is reflected. So we don't see those colors. And we see the eye over here. And the brain gets when these green waves hit the green cone cells, inside them there's molecules that jump around on that wave, and the brain says, oh, I see green. The book is green. And we could do the same thing for the red, right? I could have another book with a different kind of molecule, and it would be the red that bounces off, but the blue and the green would turn to heat, and we would say the book is red. So we get that for the three colors. Here's the cool thing, though. Watch what happens if two colors bounce, because that could happen too. I'm going to take this book, and it's going to be a yellow book. Different molecules. This time these molecules are yellow. Now here's what happens. The red comes in, and the blue and the green are all part of the white light. And so what happens here is the blue light is absorbed. Blue turns to heat. But there's molecules in here that can bounce the green and bounce the red. So we get two colors reflecting, and the blue turns to heat. It's absorbed. We can't see it. What does the eye do when it sees two colors at the same time? Well, that means that in the eye, both the red and the green cone cells start to get excited, and they both send a message to the brain. And the brain says, oh, well, here's the weird thing. The brain says, if I get a message from both, I'm going to call that yellow. And the brain sees yellow. Yellow is actually a mixture of red and green light, which doesn't make sense, because if you take red and green paint and you mix them together, they don't make yellow. But that's because we're looking at it from a different perspective. Yellow is what the brain interprets from its signals when the red and green retinal cone cells are stimulated. We actually see yellow. Okay. So if we look at what's reflected, if we go back and we keep track of what's reflected, we saw that if you reflect blue, you're blue. If you reflect green, you're green. If you reflect red, you're red. And those are the primary colors because you only have to reflect one color to be that color. But if you want to be yellow, you got to reflect red and green. Then you become yellow. What happens if you reflect a different color? Let's see if I can find something like this color. This color is kind of a bluey green. We call it, I don't know if you know the name of this color, we call it cyan. That's its name. If you know anything about printers and printer ink, you often use a cyan in your printer ink, right? And it looks almost that color, as close as I can get right now. I suppose I could find a better color if I went here. I could make a color, but I think that'll do the job. It's close to cyan, right? Let's just leave it at that. We'll call it cyan. So what's happening here? Well, red is coming in, and blue is coming in, and green is coming in. What's happening here is the red is being absorbed, turns to heat, because there's no molecules that have the right kind of electrons in the right places to jump up and down to make that reflect. Okay, now the blue gets bounced back, and the green gets bounced back. And our eye then will see our blue and green cone cells will light up at the same time. And when our brain sees them together, our brain says, I see cyan. Right? I see oops, I can't spell here. Cyan. Blue and green make cyan. Up here, we'll put I see yellow. And then lastly, if we look at the option where instead of red and green or blue and green, what if red and blue are reflected? We can draw another picture. If red and blue are reflected, we get a nice sort of purpley color. I'm going to try to find a better version of this. More like this. It's like a darky pink purple. This is closer to, well, whoops, didn't listen to me. More colors. This one. Okay, I forgot to press OK. Let's use this book or this object. What color do we call that if you think about colors? Anybody know? Magenta. It's like a pinky purple. Magenta. It's also in your printer ink. Magenta. And we're going to learn why your printer uses these weird colors instead of just like red and blue and stuff. We'll see that later. So what's happening here is red is coming down, blue is coming down, green is coming in the white light, but green is turned to heat. The molecules here are different, and the green turns to heat, so it's gone. And the only thing that bounces, because the electrons are just right to jump up and down for this, is the red and blue. And then the eye sees, again, what's happening is the brain is getting a double signal. Instead of getting just a red cone cell, it's getting a red and a blue at the same time. And it sort of says, okay, if that happens, I see magenta. So what's actually happening here is the brain is interpreting what happens or what color to see when two different rays hit at the same time. Now, what's interesting, too, is that the magenta makes sense because if you think about red and blue together, it kind of looks like it might make a magenta color. And if you think about blue and green, it kind of makes a cyan. But there's no way in your brain you can imagine how red and green make yellow. And that's because that's not a good way to look at it, okay? Because it's not about mixing paint, it's about reflecting light. Our whole focus here is focusing on which light is bounced off, which light is reflected, okay? We don't really care about what turns to heat because it's gone, we don't see it. So when we see light, we are focused on the light that is reflected. And when we focus on that, we have a name for it. Let me go down a little bit more. When we focus on the light that is reflected, the light that is reflected, we call that the additive theory of color because we're adding light together. The additive theory of color, okay? When we focus on light that is reflected, we call it the additive theory of color. Now, we'll summarize all the pictures that we've drawn. So, in the additive theory of color, there are three primary colors. And they are red, green, and blue. Then, if you mix those reflected colors, if you see more than one reflected color at a time, we can mix them together. The red mixed with green produces what we see as a yellow color. The red mixed with blue produces the color, so those are a mixture, right? Red and blue. That produces the magenta color that I used, magenta. And then lastly, we can have the the green and the blue mixed together. So we're seeing two kinds of reflected light, the green and the blue, and that makes the color cyan, the bluey green color. Or teal, maybe teal. If you think about the color teal, it's almost like that. Because yellow and magenta and cyan are made from two kinds of reflected light, we call them the secondary colors. I'll write that word out, secondary colors. Primary colors are made of one reflecting color, whereas the secondary colors, and there's three of them, are made from mixing two colors. Now, the process can get more complicated because you can also mix 3 colors. What happens if you mix red, green, and blue all together? Well, if you think about it, that's how we started. Red, green, and blue all together is white. So if you mix all 3 colors together, you get the color white. Now, well, you get white, which really isn't a color, but a mixture of colors. Right, so we're going to put down all 3 colors together. Let's write it here. Red, green, and blue mixed together. Red, green, and blue make white. Now, of course, that's not true with paint. You can't mix red paint and blue paint and white and green paint and get white paint. It seems backwards. But that's because paint doesn't work with this story. This story is focusing on the light that is reflected. We ignored all those little bits of light that turned into heat. Okay, so far so good. Now, that's the additive theory of color. It has 3 primary colors, red, green, and blue, that allow us, to our eyes, to interpret all the colors of the rainbow with just these 3. Now, you can mix them. What I'm talking about here, when I say you get, green and blue make cyan, I'm talking about mixing them in equal amounts. But it's possible to get different shades of these colors by mixing them in different amounts. So for instance, let's say something wasn't, let's take a red and blue. What happens if you get something with lots of red light and only a little bit of blue light? In other words, it's not in equal proportions. Well, red and blue is supposed to make magenta, but what this would make, it would make a more redder shade. In your eye, there'd be more red cone cells firing than blue. And this would give you a darker shade of magenta. So maybe it would start to look a little more like this. Maybe it would be a darker shade of magenta. So if you mix them in not equal proportions, you can get all the different sort of in-between shades of these colors as well. But that's a little bit complicated. So we usually just think about mixing them equally to get these 3 colors, the 3 secondary colors, and that's what you would get. Now, interestingly enough, we know this works because this projector that I'm looking at right now, that we're all watching, and the screen, if you're watching this on the computer, the screen of a computer looks like this. If you use a little magnifying glass and you turn on a computer to a white page like this, in fact, I bet you I can do it. You won't see this on the video, but you would see it. You would see it maybe from where you're sitting. If you look, this is actually so small, even my magnifying glass doesn't see it. What there are pixels on the screen. Pixels are the tiny little lights that make this whole thing show. And you wouldn't believe it, but the pixels are arranged. Let's say this box is a magnified version of my white screen here. There's a red, a green, and a blue in the pixel. And beside it is another one. Red, green, and blue. And this goes all the way along, so there'd be like millions of these little pixels, well, let's say thousands of these pixels all along the board under a microscope. The electrical signals can light up these pixels. So let's say on the screen, over here on this region, there was a blue object. And if I zoomed in, the pixels, I would see that the electrical signal was only lighting up the blue pixels, making the blue shine. So in that part of the screen, it would look blue because the red and the green are off. The electrical signal is not turning on those pixels or lighting them up. But if this part of the screen was green, it would light up the green, right? Or light up the red for a red object. If there was a yellow object, it would light up the red and the green together in the same amounts. If there was a magenta object, it would light up the blue and the red together in equal amounts. Or if you had a whole bunch of these pixels, right? The computer could light up some of the greens, but more of the blues and no reds, and you'd get sort of a dark bluey shade of cyan instead of the bright cyan that we use. So the computer, electrical signals in the computer can light up on the screen all the different sort of combinations of red, green, and blue dots and produce all the colors that we can see on the screen. So when I look at this mix of colors here that I'm showing, there's yellow and there's greens. All of those are made by lighting up different amounts of blue and red and green dots. That's it. That's all there is on there. Now on this screen, you can't see them. They're so small, you can sort of see a hint of color, but on a television screen, right, if you hold a magnifying glass up to it, when it's turned on and you can find a channel that's not like off the air, like just fuzzy snow, and put your magnifying glass, you'll be able to see all the little red and green and blue lights. When I look at it, I see white. Why do I see white? Because the screen is lighting up all three, red, green, and blue, at the same time, and our eye sees white, the mixture of colors. So this board is not white. If you zoom in on with a microscope, it's really just red, green, and blue dots underneath all this that are shining equally, but that mixes in our brain. We call it white light. So what we are doing in the additive color theory is we are adding the colors of reflected light. That's the key word, of the light that's bouncing off. Okay, remember that. The additive theory is what you get when you add up the reflected light. And that's why TV screens are RGB. We see the red, green, blue. They all operate on the same principle, red, green, and blue. And those are the primary colors of the additive theory. Now, the art students will say, okay, well, I thought blue, red, and yellow were the primary colors. Well, to understand art and the mixing of paints, we have to look at this from a different perspective. We have to look at the subtractive theory of light. And instead of looking at what light is reflected, we will focus on the light that's turned to heat. But we'll do that in our next little video or lesson. So we'll stop here.